Hello, this is Tom from antiproton.com, and I don't know if you can see the smoke coming out of my mouth and out with steam, but I am actually outside right this moment. I have no idea why I'm outside, I just am, and you might be able to hear it. There's an ice storm behind me. I thought I would talk about the speed of light, the closest star, and the problems getting there. First off, did you notice that? I have ticks, see? Tick disorder. Thanks, Tourette's. Anyway, the closest star to us, of course, is our own star, 8 light minutes away. That means that at 3 million meters per second, that's 3 million meters every second. It would take about 8 minutes to get there. For you sciencey folks, that's 3 times 10 to the 8th power. It's a lot. Anyway, the closest star beyond our system is probably, I think it's Proxima Centauri or Alpha Centauri. So anyway, they're about 4.25 light years away. That means it would take you 4.25 years traveling at 300 million meters per second. That's 186,000 miles every second. It would take you 4.25 years to get there. Isn't that creepy? That's maybe not too long, though. I mean, it's only 4 years, 5 years. So who wouldn't get in a cryo chamber for 5 years and journey to another star? It seems like a great, fantastic idea. But here's the problem: how long will it take you to get to the speed of light? Well, this is kind of a calculus problem, and we're not going to go into calculus right now. But consider for a second that if you spend a year getting to close to the speed of light, then all that time that it was taking you to get to the speed of light, you're not actually there yet. So it's going to take you longer than 4.2 years to get there. It's going to take you, several years to speed up. Then you also have to use the same amount of time to slow down, because you don't just hit the brakes. I love that in TV shows. It takes them a while to speed up, but then they just instantly stop when they want to. And of course you don't. It takes you a while, equally as long, to slow down. Anyhow, let's say you journey to another star system. You've calculated that you can speed up and you can slow down, and you think it will take you 8 years to get there, for instance. Let's just say. The amusing thing is, when you actually got there, you would calculate that if you were traveling, let's say, 99% the speed of light, you'd calculate that only a small amount of time had gone by, maybe 3 or 4 years, and you're going to say, wait a minute, hold on. 3 or 4 years, how could that be? Well, apparently, the faster you go, the slower in time you go. As you approach the speed of light, you approach, almost no time going by at all. This is called a Lorentz factor. God, it's cold out here. Freezing to death. Anyway, what it comes down to is the closer you get to the speed of light, the slower your time goes. And it goes like a curve, one of those little curves, you know what I mean? It's called an asymptote. And basically, at 10% of the speed of light, 20, 30, 40% of the speed of light, you don't notice much of a difference. The clock's running maybe 30 seconds slower or whatever over the course of a couple hours. But as you hit 90%, the curve gets greater and greater and greater and greater and greater. As you approach the speed of light, 99.99999% the speed of light, your Lorentz factor becomes really high, so that a year on Earth could be a week on your spacecraft, maybe even less. Isn't that crazy? So anyhow, interesting things to think about. You might go for a 20-year mission to another star system, and you come back 20 years more, and you think, wow, I was 20 when I left, 20 to get there, 20 back, I should be 60 years old, and you are. But when you get back to Earth, you find out that it's been 400 years or 200 years or something like that. They don't talk about that in sci-fi shows. So the point of the matter is, getting to another star system is perfectly feasible, but we'll need some faster-than-light technologies if we want to do it practically. Because feasible, practical are different things. Anyhow, that's what it boils down to. Now, why does light move so fast? Light moves so fast because it effectively doesn't have mass. It may actually have mass, but probably not. And remember, as your speed approaches infinity, doesn't approach infinity, excuse me, that's incorrect, mathematicians would beat me. As it approaches the speed of light in a vacuum, the energy required to go faster kind of sort of goes up a little bit with that equally. Anyhow, that would be the reason that in Geneva they're trying to find the Higgs boson particle, because that might reveal a little bit as to why that occurs. Anyhow, the Higgs particle is sort of strange. It has a tendency to, in theory, attract itself to other particles that have mass, massive particles, or energetic particles, which would explain photons. But anyway, enough of that. The point being is you have mass, so you can't go the speed of light. Sorry. Well, you could go the speed of light, but it would take like nearly infinite energy, and as you got right up on it, you'd hit a limit. Remember limits for math class? Yeah. So the limit as you approach the speed of light is, well, not so good for you. You need a lot of AA batteries. Anyhow, that pretty much sums that up. So, yeah. Have fun building your spaceship. Peace.